I'm Enrique Bullfried, talking to you from the Marine Science Institute of Andalusia and the Spanish Council for Scientific Research. I might talk on the potential of ontologies for the empirical assessment of machine learning techniques in operational oceanography. The goal of this contribution comes from ontologies are needed which provide a domain to the marine community for improved data visualization, and also because our approach fosters reusability of the data in order to connect a given data set to domain-specific ontologies, and thus to make it more understandable for the diversity of communities of practice in oceanography. There is a central goal in seeing the use of ontologies for representing databases entities, and it is that makes especially advantages in the field of operational oceanography. There is a key phrase from Jean Delaney that underpins several ideas in the third goal. There are emergent technologies throughout the fields around oceanography, which we will incorporate into oceanography, and through that convergence, we will make oceanography into something even more magical. Those techniques are artificial intelligence, neural networks, ontologies. Apologies. So what you can see here is a visualization of the CICE ontology on Protege. CICE is an organism in the European Union connected with maritime services, mostly in the security area, where central classes of the CICE model concerns the location entity. By here, you can examine the context and situation, how the context and situation are intertwined concepts. The maritime situational awareness heterogeneous sensor network ontology extended to support entity profiles and event context. Boxes represent top-level ontology concepts, including sensors and observation in violet background. Observation values, light blue, and maritime events, orange. Arrows represent object properties linking concepts. Empty boxes are concepts from existing ontologies. A representation of the overall structure of the core ontology for the cooperation of underwater robots, SWAN's ontology, the details of which of communication ontology that can be used by remotely operated vehicles to transmit data and commands between vehicles and operators is defined by all in SWAN's platform. SWAN's users can estimate the rate of spread of pollutants and determine the level of pollution and the estimated size of the polluted area. The ENVO ontology is linked with ontologies for coastal features, services, and roles for emergency response, like SWIFT, as a contextual ontology standardizes environmental classes to systematically track sample origin. Environment ontology bridges domains with increased scope, semantic density, and interoperation. When the cruise ODP was created, actions to connect the relevant concepts within that pattern to the aforementioned trajectory pattern were specified. For example, action 1 shows that the cruise has exactly one trajectory and is undertaken by exactly one vessel. The research agenda of this contribution guarantees the operational oceanography approach to cope with uncertainty estimates and is impacted by emergency conditions related to oil spills, discharges of untreated or improperly treated water for treatment plants, intensive shipping, and secondary pollution. The data-driven future in marine sciences is conditioned by the absence of interoperability. If every laboratory making these measurements composes their own text string, the richness of expression would be so great that semantic interoperability would be an impossible dream. The approach to this problem is to use a semantic model to break down the information content into discrete items, each of which is itself a controlled vocabulary. But as a control is that there are not enough data. Data consumption for oceanography data are broader in scope beyond the research project-based synoptic studies that tend to fund research cruises. A major additional consumer is the increasingly data-hungry family of ocean forecast models that require low-grade versions of data less than 24 hours after observation. Up until the 1990s, ocean data were only available once a research cruise had reached port, and the physical media, tape, disk, etc., had been submitted to data centers. Also, the few annotations in images. A positive aspect of analyzing terms uses in annotations will be that possibly this could pose a bridge between the two worlds of formalization and representation, since an interesting approach would be to ground this activity in controlled vocabularies or ontologies. Use cases are unpredictable due to the unpredictable and sometimes hostile nature of the marine environment. The capture of marine data is frequently challenging and requires a significant amount of resources to be invested. The data captured is also often unique, providing an unrepeatable measurement of the state of the ocean at a given moment in time for a specific geographical location. Marine data is therefore irreplaceable and extremely valuable for future research. It should therefore be made as widely available for reuse as possible. Addressing the application of ontologies in ocean data grows out of an artificial intelligence engagement with marine data metrics of interoperability and reuse. Ontologies serve as such a tool and methods to assess the added value robotic technology brings into the marine environment, autonomous underwater vehicles, or ocean floor observation systems. From a pattern recognition point of view, ontologies for describing sensors and sensor networks work in the context of sensor web applications. Knowledge representation in the Internet of Things presents a general architecture of sensor web applications, and that is why it provides huge numbers of interconnected data across an extended variety of various ocean regions, which classifications depend on the specific context and resources of linked data. Facilitating system interoperability through data harmonization, ensuring interoperability between marine databases is a huge challenge. Terms and codes used to structure exploit the data comes from many sources and are continuously evolving. There is a need to define sustainability criteria that can be used in data documentation assessment. Ontology utility features for efficient object detection in the seas and oceans focuses on tasks such as object detection, data recognition, and multi-level data classification. A special triple will be generated with RDF type property and the fixed SSN sensor as object, providing a consistent set of terminology, domain vocabulary, and concepts in the robot's knowledge representation, definitions, relations, domain axioms, and taxonomy. It is the ideal tool when we focus on the generation on textual descriptions for images in 3D shape retrieval, for example. Axioms and formal declarations can help to recognize when data have been entered incorrectly. For example, one of the actions in the cruise ODP is that the cruise involves exactly one vessel. If a single cruise has two vessels associated with it, those vessels must actually be the same ship, or there is a mistake in the data. This is a proof of principle study, and it explores the contribution of ontologies to marine data potential, a fine-grained categorization of sensors and observations or representations, such as provided by a specific ontology, is a prerequisite to advanced functionalities that may arrive to favor features such network performance. A transnational network for data exchange would profit with this increases interoperability by working in real time with relatively few and well-controlled formats. Using science-driven use cases focusing on vocabulary alignment ontologies provides cube data to assess the added value of marine technology. An increased level of validation for individual data values is a quality flag for dimensional data visualization. Ontology topics can be followed from different perspectives. The index is the percentage of the publications on ontologies for areas of research. The initial synthesis was accomplished by deciding on a uniform list of metadata and their distribution along the years, as found in this slide. It covers semantic web services, and so forth. Especially the semantic web, data integration, and web services have attracted the attention of a large number of researchers in recent years, while the research on data sets, relation extraction, and heterogeneous data seems less consistent. One element is the major cause of this problem. As far as an ontology for marine data is necessary to enable exchange and integration of data, terminology used to describe similar data vary between marine specialties or world ocean regions, which can complicate data searches and data integration. The ultimate goal of this slide is to show a system that combines visual and textual semantics to regularly annotate video sequences with the appropriate keywords of a domain expert that will link the visual and text semantics. Because a map already populated with data and information is very difficult to be changed in a later stage, because that possibly means moving information across nodes, which of course cannot be automatized. These definitions are the necessary definitions to start with, because they are partitioned into mutually exclusive cross-product sets, many of which reference other candidate ontologies for chemical entities, protein, biological qualities, and zoological entities. An example of such case is the environment ontology, which, using the expressivity of all, grows in acceptance and participation in new user communities, thus offering an example of ontologies classes increases granularity in their logical definitions, allowing more flexibility in semantically advanced questions, inferences, and analysis. We need to interpret remote sensing images. What visualization process optimize is the availability for reuse of data to deal with uncertainty in quasi-empirical models. And an example is by using the cascade automatic annotation server, and it comprehends the advances of ontologies interpreting satellites. The fourth point is useful to highlight the existence of a gap between what is required by stakeholders and what can be offered by experts. This is not only a gap, but a structural difference. The main focus of stakeholders is on nouns, decisions, and protocols, while scientists offer observations and hypotheses. And the fifth point, marine ontology feedback, presents a substantial positive bias to the domain of visualization. 85.7% of the ontological context detected in the data sources analyzed in this contribution. Ontological context detected in the pattern analysis, data classification, and data recognition in data sources that was analyzed, a substantial positive bias in ontological feedback to the domain of visualization was detected. 85.7%. Subsequent approaches for visual events were larger than in the case of the second scenario, marine learning, and in 80% cases, researchers proposed model development to cope with marine transcriptome genome identification. They used the gene ontology, GO. This is the final workflow of this presentation, a particular process to prove the feasibility of ontologies for sensor data fusion. It has been obtained in 4 main steps: obtaining ontology research trends, reviewing the previous research and application of pattern analysis, identifying marine data classification and recognition issues, searching for pattern analysis and machine learning parameters to encode for a large part of the ontology's semantic content. These 3 long-scale histograms are A, 25 top metadata required with pattern analysis, captured data to detect, recognize, and identify targets of interest from physical, optical, fluid, and chemical underwater parameters. B, histogram estimations by images or by video parameters with an emphasis on multi-level data classification. C, ranking title terms metadata of the documents on data recognition. To investigate whether a data visualization level can give a prediction of its suitability for a particular machine learning task, in the first table, machine learning data visualization techniques were approached through metadata generated from a base histogram and classified into 4 levels: disseminative, observational, analytical, and model developmental. The spectrum of different steps of visualization ranges from high abstraction levels, example model development tools, to lower levels, example operational aids. Only 16% human analysts need to use visualization to observe data routinely. We can further derive from that deep learning is the main automated support of marine data analytics using machine learning techniques. Perhaps this is caused by the success of deep learning in computer vision tasks, in image classification, object detection, instance segmentation. Analytical and model developmental visualization levels were shared equally among other machine learning techniques employed, as the number of papers published by years. Years 2020, 55 papers published, and 2021, 48 are peaks. This is not a strange sense. The idea that in machine learning, pattern analysis is gaining future is expressed again by the importance of the 2 last years for the 4 levels of visualization, relative importance of 69, 17, 44, and 43%. As expected from the results in previous table, we have gaps in both disseminative and observational data sets, with 6 years breaks in between. The ontological and machine learning datasets present undistinctive features. They have been expressed through box plots by using logarithmic citation weighted counts. We found differential expressions of how their values are spread out and detect schematically their outliers. According to the data value and methodological choice, 2 different data classification and recognition scenarios in pattern analysis can be compared. Under the first scenario, ontology basis for image retrieval and annotation was used to derive marine date patterns. The second scenario, machine learning, as it received 70% of total citation, resulted in that its lower quartile of 0.45 reaches a best score for machine learning than for ontology, 0.38. This study focuses on characterizing marine ontologies to select data visualization techniques. The underlying assumption is that the application of ontologies in marine data poses the problem of how should marine databases be represented. A data histogram approach has been adopted, which draws on the analysis of licensure until significant categories appear. The results of the model to predict what the encoding for a large part of the ontology's semantic content is going to look like in the future show that marine ontologies' specific coverage statistics are few. It is acknowledged that the biomedical gene ontology currently represents the most successful implementation of ontologies in the domain of oceanography for pattern analysis applications, including data visualization. The potential of ontologies to support the generation of model scenarios for image retrieval and annotation to aid for the empirical assessment of machine learning techniques is to be encouraged. Marine model developers should improve their efforts to improve data discovery, sharing, and integration on the base of ontologies. Thank you.